membership information will be going out soon in the mail. Please support them so that they can keep doing good works like this. And now I am going to turn things over to William Quinn, and I believe he will be making the introduction for our lectures today. Thank you so much.
Thank you, Mrs. Hanson. So today, our topic for today is going to be mathematical probability. Before we begin, I'd like to thank MC Squared for arranging these. In particular, Roger Van Peski for attending. And then, therefore, without further ado, Roger Van.
Hi everyone. So, can everyone hear me in the back?
Yeah.
Okay. So, I'm Roger Van Peski. I'm a junior math major at Princeton, and my talk today is called Paradoxes, Probability Theory, and How We Understand Randomness. Now that that's out of the way, there's this. So, in the beginning, I'm going to talk a little bit of sort of more philosophy than math about what we actually mean when we talk about probability theory. Don't worry, this is only about 5 minutes. Then I'm going to talk about a problem, which I'm going to ask you guys to more or less solve, but there'll be help, which sort of highlights a common error that we can make in thinking about random things, and sort of why the approach of probability theory is necessary, or at least is a way in which we can talk about randomness. And so, first I'll ask you a question which I think some people should be able to answer. What's the probability if I throw a six-sided fair die that it comes up as a 6? Anyone? You can, okay, you in the front. Mm-hmm. So what does that really mean? Yeah?
That there's 1 out of 6 chance that it'll land face side up a 6.
Okay, so but if I'm going to throw this die, like what does a 1 out of 6 chance mean? You.
Well, if you throw it 6 times, there's a pretty high chance that it's going to land on a 6 at least once during my 6, I guess.
Okay, so what if I have a special die that always throws 1, 2, 3, 4, 5, 6, and then repeats? Was there a 1/6 chance on the first throw?
Yes.
No, but I'm saying like on the first throw it's guaranteed to be a 1, second throw it's guaranteed to be a 2,
No.
etc.,
No.
and then it repeats. So then that's not quite random. That's not what we mean by random. Does anyone else have an idea of what this means? Yeah?
For every given throw, the possibility of coming up with a 6
Yeah, it's a hard question. This is a question that people think about and they're not entirely sure about, especially if they're like philosophers of quantum physics or whatever. Yeah?
every outcome has an equal chance and
But you still use the word chance. What does that word
as
mean?
in is equally likely to be chosen.
What does likely mean?
Does anybody have a Webster's dictionary here?
I think that's also going to be pretty circular. So the point is that we don't really have a good idea of what this means. You could say, okay, if I throw it a lot of times, then about 1/6 of them will be 6, and there's no obvious pattern like 1, 2, 3, 4, 5, 6. But then, okay, what if you look at the digits of pi? So we know that like these digits are distributed evenly among 0, 1, 2 through 9, right? So if you pick a random, let's say the 1000th digit of pi, if I don't know what that is, and I don't know what that is, then as far as I'm concerned, that has a 1 in 10 chance of being a 6, right? But let's say you do know the first 1,000 digits of pi. Then as far as you're concerned, that either has a 0% chance or a 100% chance, depending on whether it actually is a 6. So back to the dice. Let's suppose that we get a bunch of, I don't know, engineers, physicists, whatever, in the room. They have a bunch of instruments. They can analyze your throw, and they can see, they can like get the position, momentum, spin, whatever on this die, and they can tell you, okay, we're 100% sure that this die is going to land up a 6. But you don't really know that. So is that random?
No.
So does randomness mean that it's actually random? Or does it just mean that you don't know what's producing it? This is just something to think about. You can hold that thought. It's not a question that has a really good answer. Maybe in quantum mechanics, but I don't know enough quantum mechanics. But this is worth thinking about. What do we actually mean when we say chance, when we say likely, when we say probability? And so, yeah, that's what I'm going to be talking about today. Trying to sort of say one thing we could mean in a mathematical formalism. But it's always important to remember that probability really is meant in some way to model so-called random events. And in some sense, we should think about how this actually corresponds to the events that we think are random. Okay, so yeah, that's everything. Okay, so now the problem, I promise. So this is something known as the two envelope paradox. For a show of hands, has anyone heard of this? Okay. So, okay. Here's the paradox. So I have two envelopes. One of them has twice as much money as the other one. You don't know how much money either of them have, though. You just know that one is double the other. So let's say I shuffle them behind my back and I give you an envelope. This has, say, 50-50 chance of being the one that has twice as much money as the other, or being the one that has half as much money or the other. And then I give you two options. You can either open your envelope and take the money, or you can switch your envelope with the one I still have, open it and take the money. Which one would you choose? Does it matter?
No.
Why not? Yeah.
Because there's still 50-50 chance that you can get either one.
Mm-hmm. So you're saying basically it's symmetric. You could also think of it as I just put one in each hand and then you chose which hand, and it's fairly easy to see that that's symmetric. Okay, yeah. So now let's change the game slightly. I have these two envelopes. I give you one. It has a 50-50 chance of being the one with double the money or the one with half the money. I give it to you and you open it, and it has $20 in it. Now what do? Do you switch? All right, I'm sorry. So I changed the game. I give you the envelope. You can open it, see how much money is in it, and then you can choose to either take it or to switch it with the other envelope, which you don't know.
It's like those
Yeah?
It's like the long.
I think that if you're just like looking at what would get you the most amount of money on average,
Mm-hmm.
I think that switching it would always be the better choice. Because in this instance, you had 20. If that was the better one, then switching it would get you 10. And if you had the worst one and you switched it, it would get you 40.
Mm-hmm.
And so the average of 10 and 40 is 25, which is $5 more than what you have with 20.
Okay. Yeah, I think that's a pretty convincing argument. So his argument is that you should always switch if you just want to maximize the sort of the average amount of money that you get out of this game. Like, let's say you don't have any kind of diminishing returns. Like, money matters less to you if you have more of it. You just want to maximize the average amount of money that you get from this game. So, okay, so his argument then is that if you open the envelope and you see it has $20, you should always switch, right? But there's no desperation for money. This is just like you just want as much money as you can, and money means the same thing to you no matter how much you have of it. It's not like you just want to maximize the money. Okay. Yeah. So his argument is that you should always switch for if you see $20, but the same argument says that you should always switch if you see any amount of money in the envelope, right? It's the same scenario.
Unless
So-
you're positive that you,
Huh?
more.
Well, the way we've set up the game, how would you be positive?
You can have mind control. You can read minds. You can read minds.
You can't read my mind, it doesn't work. So, okay, so if you take that argument and take it to its logical conclusion, then when we go back to the first game where we didn't open the envelope, we know that if we opened it, no matter what we saw, we would want to switch, right? So then we should switch. But then that doesn't really make sense, because I thought your symmetry argument was fairly convincing that it doesn't matter whether we switch or not. So what's going on here? Does anyone have any ideas? You in the back?
I think that if you're playing it multiple times, then if you always switch, then yes, you will on average get more money. But if you're just playing it once, then it doesn't really matter what you did.
If you're playing it multiple times, why do you think that's true?
Because there's a 50-50 chance of having the envelope with more money, right?
Mm-hmm.
So if there's another envelope and it either has 2x, in which x is the amount of money in your envelope, or 0.5x, then on average, it will average out to 1.25x if you keep picking that one. Whereas if you only pick it once, it will either have 2x or 0.5x. You don't know which one.
Okay. So by that logic, if you play the first game where you don't see what's in the envelope and you play it repeatedly, then you should also keep switching, right?
Yes.
Do you think that makes sense? What do you think goes wrong with the symmetry argument then?
It's just that the material value of 2x compared to 1x is greater than that of 1x compared to half of x.
Right. Yeah. No. Like I get that argument, but in the original game where you don't see the amount in the envelope, like do you think that there's a flaw in the symmetry argument that so the symmetry argument was you don't know what's in this envelope, you don't know what's in this envelope. You can choose whether to switch or not, but then you're basically just choosing this envelope or choosing this envelope. And you don't know anything about either envelope, so it doesn't matter which one you pick. Do you think there's a flaw in that?
Well, I think that the second envelope, like if you just assign variables to it, like if x is the amount of money that you have, and then
The amount of money in the envelope that you were
yeah,
given.
and yeah,
Okay.
then then you will always have, like, even in that other, even in the first game, you'll have X amount of money in the envelope that you chose. So I think it can be applied to that one.
Okay. How about the rest of the audience? Do you agree? Do you think that it makes sense to switch in the case where you don't open the envelope? Do you think that there was something wrong with the argument that you should switch if you open the envelope? What do you think? Yeah.
Well, personally, oh, stop laughing, will you? So personally, it's like this two envelope paradox. Basically, it's like if I pick the envelope, there's a 50-50 chance, 0.5 or 2. And if you average it out, like you said, it's 1.25. And while I don't have the solution to this, I do have well, I don't know how to say it.
Okay. Does anyone else know how to say it or something else? Yes?
I think the symmetry argument is only valid for when you don't know how much
No.
money.
Oh, I have it. Oh.
But why do you think that's true?
Because when you know how much money is in the one envelope, then it gives you a bit more information, and that changes the chances.
How do you think it changes the chances?
Yeah.
You can't change chance. Well, it just does.
Okay, so that's an interesting idea. So what he's saying is basically, if you open it, then you should consider the amount of money that you see when you decide whether or not to switch. I think that's what you're saying. So, but how should that amount of money affect whether to switch? Because I think, sorry, what's your name?
Liam.
So I think Liam's argument that there's a 50-50 chance that that the other one has half the money or twice the money. Why does the amount of money that you see when you open the envelope affect that argument? Any ideas? Yes, in the back.
If you see a good amount of money in the envelope that you have, you're less likely to switch because you don't want to risk having half that money.
But you could get twice that money. That'd be a lot of money. Yeah, we're assuming though that you're not risk averse. Like if all you care about is the average amount of money that you win, and let's say that you're so rich that this amount of money doesn't really have a personal value. It's just a number, so you don't care. All you want is to maximize your average money, but it's not like, oh, I don't want to gamble because then I can't get my car fixed or something. Yeah. Yeah.
So I think that it's the symmetrical one is the correct one, because let's say we change the paradox so that, let's say you give me an envelope and you show me what's in your envelope, then it doesn't really matter which, like with the idea that you get an average of more money, then would it still follow that if I see your envelope that I'd want to switch to my envelope? Well, that I'd want to keep my envelope or go to yours?
So I think what you're saying is the sort of the logical conclusion of this argument is that if I show you the amount of money in one envelope, you should always pick the other. It doesn't matter whether I show you the one that I put in your hand or the one that I still have in my hand. Just whichever one is unknown is better.
What I'm saying is that it doesn't always makes sense to switch, and you don't know which one will be the higher, which one will be the lower. So,
So you're saying you don't think it's just a 50-50 chance the other one's higher or the other one's lower?
I think that it's an even chance that either one is the higher one, or either one's the lower one.
But then if it's an even chance, then you have 50% chance of gaining the amount you have again, and 50% chance of losing half the amount. So on average, it's still better to switch, right? Still better to pick the unknown one, if you know one but not the other. This is a hard problem.
Is it open to grown-ups too?
Yeah, sure. It's been long enough.
I think it works out the same way. The
What do you
reason
mean?
is, initial argument, some of the kids, what they said was, let's say the envelopes are $20 and $40,
Uh-huh.
and but you don't know that. Let's say you pick $20 bill. Now you guess the other one could be 10 or 40.
Mm-hmm.
So when they did the argument, they took X and they said, I think they averaged it between half X and 2X.
Mm-hmm.
But the assumption there was that we are picking the smaller one, I think. You could also have picked 2X, in which case the average would be different. If you pick X, I don't know.
So I think what you're saying is, if you knew in advance whether the envelope you had was the bigger one or the smaller one, then you would know whether or not to switch.
You would know, then it doesn't.
Yeah.
There is no,
But the thing is, you don't know whether the one you have is the bigger one or the smaller one. So then you have to decide. You have to sort of average over the possibility where it's the bigger one and the possibility where it's the smaller one, in some sense. Okay, yeah. So I think this was hopefully enough to convince everyone that this is a pretty hard problem to answer. It's very counterintuitive. But I'll talk a bit about how probability can help you think about it. So, okay, so let's sketch the two arguments. So first we have the scenario where we don't open the envelope, and the one where we open. So in the one where we don't open the envelope, we have the symmetry argument, right? Which is, I gave you one, it had a 50% chance of being the bigger one. You don't know which is which, so you could, whichever envelope I gave you is in no way, like the fact that I gave it to you doesn't put it in a privileged position. It's just, you're just choosing one of the envelopes. The fact that I offered one to you and then let you switch was sort of a meaningless part of the setup. You could just think of it as I offered two and you could pick either one. So that's the symmetry argument. So that seems like a fairly convincing argument that it doesn't matter. So now in this case, so we opened one. So let's say we assumed here that you have 50% chance you get the bigger one, and 50% chance you get the smaller one, right? So this is before you've opened the envelope. So now if we assume that this is still the case after we've opened the envelope, then I think, and hopefully you all agree, that if this still holds, you're better off switching, right? Because if you're just like the same argument that we've been talking about back and forth. If yours is smaller, you have double the amount to gain by switching than the amount that you have to lose if yours is bigger. And so if it's still 50-50, then you want to switch. But then this led to a contradiction here, because then you would always want to switch. And so if for instance I then given you the option to switch back, you would want to take that, and then you would want to switch back, and then you would want to switch back. And something about that seems very nonsensical, to me at least. So let's look at this assumption that there's still a 50% chance that your envelope is bigger and that your envelope is smaller after you've opened it. Before you've opened it, like, we assume that this is true, that's out of the question. After you've opened it, however, we're making a bit of a leap to say that that's still true. Because maybe the amount that was in that envelope affects whether it's likely to be the big one or whether it's likely to be the small one. So, for instance, let's just say that I give you a bit more information before the game. I said one of these envelopes has either $10 or $20 with 50% probability, which one, and then the other one has double that, so either 20 or 40. So then, if you knew that in advance, and you opened the envelope and saw 10, you would know that you should switch, because you would know that the other one didn't have 5, it had to have 20. And likewise, if you opened it and you saw 40, you would know that the other envelope couldn't be bigger, and so you should just keep that one. If you opened it and saw 20, you would know that it was 50-50, and then the argument that we've been talking about would still apply, and you would want to switch, because the other one had a 50% chance of being 40, 50% chance of being 10. So if you knew in the beginning how I was choosing the amounts of money in these envelopes, then what you saw when you opened the envelope would affect how you play the game, right? Does that make sense? So what this means is you can understand a lot better what a random amount of money means if you have some idea that it comes from some probability distribution of amounts of money. So what I mean by that is, if we just say this is some random amount of money, that's a lot less information than if we say this is some random amount of money chosen to be $10 with this probability, $11 with this probability, $12 with this probability, etc. We still don't know what the amount of money will be, but we know how it's being chosen, what sort of random process is generating it. And I think that's a very important point. Now, of course, in real life, you don't know what random process is generating a lot of things. And so if I told you at the beginning of this game, I'm choosing these amounts of money according to some probability distribution, but I'm not going to tell you what that distribution is, then you would know that there is an optimal way to play if you knew that distribution, which you could figure out if you knew that distribution. And so you would know, if you open $20, that if you knew what that distribution was, you would know whether to switch. But you still don't know whether to switch because you don't know that distribution. So in a sense, this is a kind of unsatisfying resolution to the paradox, because it says, if you knew how this money was being chosen, you could play this game. And that this switching argument isn't the right way to play this game, but it doesn't tell you what the right way to play this game is. Does that make sense? Does anyone have any questions? Yeah?
Not really a question, but kind of an opinion on this.
Okay.
Say that you just wanted to get money.
Yeah, that's what we're assuming.
Well, then I think that switching would be better because, as I said, the average of switching is better than the average of what you get. But say that you were playing, and instead of money, it was 8 coins, which you don't need at all. Say the goal was to just get more acorns.
Yeah,
I
that's,
think that in that situation, the symmetry idea would be better.
but I've been assuming, I've been assuming that we are treating money the way you're treating acorns right now throughout. Yeah, that you just want to maximize your amount of money or acorns or whatever you want to play the game with. Okay, but yeah, the point is random only means something when you have a random distribution. That's the only way that we can really understand what randomly choosing something means. And so going back to the die in the beginning, we don't really know whether this models what the die actually does, but we just say, given what I know, I'm going to define the probability that when I throw a die, it gets a 6 to be 1/6. And whether that corresponds to what the die actually does, who knows? But this is, you know, a pure die in Platonic mathematical heaven, and when I roll it, I'm going to get a 6 with probability 1/6, whatever that means. And then we try to do math in this sort of pure probability heaven and hope that it corresponds back down to the real world, which is much messier. Yes?
The next time my teacher asks us to roll a die, I'll do that argument.
Okay, feel free. I'm not your teacher. So, okay. And, yeah, are people satisfied with this paradox and how it was resolved? Resolved?
It's better than the barber paradox.
Yeah, it's a little bit, I don't know, it's still kind of unsatisfying to me, but I think it's interesting to think about. And it does highlight what I was talking about in probability theory. Okay. Yeah, so, okay. Now I'm going to introduce sort of how the mathematical framework of probability, where we have these sort of pure probability distributions that we know in advance, how it actually works. So generally we say you have a set omega, which is sort of a set of events that can happen. This is called a probability space. So you usually just label the events omega 1 through omega n. These events could be like my coin lands heads when I toss it, or like my die rolls a 6. And then we say, to each of these events, there's assigned a probability. You can see how this is dodging all the issues I talked about earlier, but that's fine, you can still do math with it. So we say probability of omega I equals something. In particular, something which is in the interval of real numbers between 0 and 1, where 1 means it's certain to happen, 0 means it will never happen. Generally, if you have an event that will never happen, you just throw it away because you didn't really need it here, it's never gonna happen. Okay, so then we say, what if I have a set of events? Like, let's say omega 1 is my coin lands heads, and then omega n is my die lands 6. I'm just throwing a coin and a die and maybe doing some other things. But these are the ones we're paying attention to right now. So then we would say the probability of some set of events. So let's say just the set containing my coin lands heads and my die lands 6, that this probability is equal to the probability that one of these things, at least one of these things occurs. So in this case, the probability that at least one of these things occurs is going to be 1 minus the probability that neither occurs. Right, so the probability that something does happen is 1 minus the probability that something doesn't happen. This is something you've probably seen in your classes if they've talked about probability at all. And then the probability that you don't get heads, so that's a half. The probability that you don't get a 6, that's 5/6. And so the probability that one of these happens is then, what, 12 minus 5 over 5. 7/12. So we can compute these probabilities and these sort of idealized probability spaces. This is something you could easily have seen in your classes. So then we say, well, maybe I want a number that depends on these events. So let's say we have a coin toss and I made a bet of $1 on it. So then we would define what's called a random variable, which is a function that takes an event that happens and spits out, in this case, the amount of money I win or lose. So then, let's say for this example, that our probability space is a very simple one. You have a coin, and it's either heads or tails. So a random variable is a function which takes some element in omega, either heads or tails, and then spits out a real number. So in this case, the amount of money that I win if I gamble $1 that it lands heads is 1. And then the amount of money that I win on tails is minus 1. And so then we can say, what's the average of this random variable? In other words, the average amount of money that I win. And so the average of a random variable, this is called the expectation value. You might have seen this as the mean, although that generally refers to data sets. This is just the sum over every atomic event, omega, of the value of x at omega times the probability that omega happens. So this is something that you guys were using back with the 2 envelopes. You were saying there's a 50% chance probability that I get double the money and a 50% chance that I get half the money, that I lose half the money. And so if we take 1/2 times the money I would win plus 1/2 times the money I would lose, then that's positive. So you were computing an expected value of the amount of money that you would win, which was your random variable. The problem was we didn't really know what this probability space was. We didn't know what the distributions were, and we didn't actually know what this probability, given that we'd seen the money, was. And so we didn't know enough for that problem. But assuming that we do know enough, this is how you write things in a probability problem. Okay, so this is the expected value. It's often written as just E of X, and it's like the average overall outcomes. It's worth noting, expected value is actually a really misleading terminology because the expected value is probably not a value that can actually happen. In this case, your expected winning is 0, but if you play the game, you will never actually win 0. So it's not the value that you expect, it's the average of the values that you expect, weighted by how much you expect them. But that takes longer to say, so we say expected value. Okay, so I'm going to talk a little bit about probability distributions. Some of these things you might have seen, some of them you might not have. So next we can say, okay, let's assume that x is mean 0. Expectation of x equals 0. But then we might want to know how wildly do the values of x vary. So for instance, if this is a gambling game, we know that if we play a lot of games, we'll break even. But how much will our wins and losses fluctuate? Like, are we betting $1,000 or are we betting $1? And so that's captured in something called the variance, which again, I think is usually taught in terms of data sets rather than random variables, but if you've seen it, it's about the same thing here. So we say if the mean is 0, if not, you have to subtract it to make the mean 0. That the variance of a random variable is the expectation of the square of the random variable. So let's suppose that we had a gambling game on heads and tails. In this case, we would have that the expectation of x squared, well, if you get a head, x squared is 1. If you get a tail, x squared is also 1 because x is minus 1. So then it's just a half times 1 plus a half times 1, which is 1. So then the variance is 1. Let's say we were playing some really high stakes coin toss gambling. And we were betting $100 on this coin toss. Okay, now this becomes, so if we win, x squared is now what, 10,000. And if we lose, x squared is also 10,000. So the variance is now 10,000. That's a lot bigger. So basically what that says is the money that we've won tends to fluctuate a lot more in this game than it does in the other game. So you can think about, well, we're talking about the mean expectation of x, the variance expectation of x squared. Well, why not keep going and take the expectation of x cubed? Now this one is a little bit harder to see. For here, by the way, for variance, you can kind of think of that. I'm going to draw a picture. If you think, you've probably seen the normal distribution, just the bell curve. This is what's called a probability density function. And what it means is if I have a random variable that's distributed according to the normal distribution, then the probability, this now has values in the real numbers rather than in the integers where I've generally been talking about. Also, our probability space is now infinite rather than finite. So I'm just going to talk a little bit about this because it's something you've probably seen, even though it's not directly using the language that I've been talking about. But when you say that a random variable is normally distributed, you mean if I make a little interval here, then the probability that my random variable falls in this interval, so this axis is just like the real numbers. The probability that my random variable, if I choose it, if I just pick it randomly, is in this interval is equal to the area under the curve here. And so if I have a small interval around 0, it's more likely to fall there because the curve is higher. If I have a small interval way out here, it's very unlikely because the curve has flattened out a lot. For those of you who've seen it, this is an integral. So now the third moment, this is called the skewness. It measures, well, how skewed a distribution is. So in the case of the variance, it basically measures how much the area under the curve is pushed out to the sides in some sense, because x squared is a function, you guys have probably seen a graph, it's a parabola. It gets bigger as you go out to the sides. And so if you have a distribution which has more areas you go out to the sides, then the expectation of x squared is going to be higher. So if you, for the skewness, the expectation of x cubed, so if x were perfectly symmetric, then if the distribution were perfectly symmetric, then the probability that you get, say, x is equal to 1 is equal to the probability that you get x equal to minus 1, right? If it were perfectly symmetric. So in that case, because 1 cubed is the negative of negative 1 cubed, those two will cancel in the expectation. And so if you have a perfectly symmetric distribution, then this measure of skewness will be 0. But if you had a distribution that instead is something like that, where you have a lot of area over here, so this means there's a high probability that you get a positive value and a much lower probability that you get a negative value, then the expectation of x cubed will be positive, because you have a high probability that you get these things which are positive 1 cubed, and a low probability that you get these things which are negative 1 cubed. Similarly, if it looked like this, the skewness would be negative. And so large positive skewness means your distribution is biased towards positive values. Large negative skewness means that it's biased toward negative values. Even though we assumed here that the average is 0. So we're assuming that the same area is here as here, but that this area is just sort of more, in a sense, more masked toward like higher values. Okay. So yeah, this is just sort of how this discrete probability of coins and dice relates to the normal curve and this notion of probability distributions that you quite possibly seen. So these are all related. So next I'm going to talk about, let's see, how am I doing for time? Is this the end of the talk? How long is this supposed to be? Okay, we started a little late. I don't know. Do you guys want to end now and have questions, or go for another couple minutes? Show of hands. Right. Oh yeah, I guess I should specify that. Okay. Who wants to move on to questions now? Who wants to not move on to questions now? Okay. I think that's the majority. Okay, so yeah, because we started a little bit late. Okay, so I'll just quickly run through another paradox, which I promised in the intro. So this is called the St. Petersburg paradox. So let's say that I have a coin, and in the beginning, you sort of have this pot of winnings. In the beginning, it starts at $2. So I flip this coin. Each time I flip a head, I double the pot. And then when I flip a tail, then I get whatever's in the pot. So I'm always going to win money. The question is how much money. So what do you think is the average amount of money that I'll win from this game? So heads, double pot, tails, take pot, stop. Yeah, behind the camera.
$3.
What?
$3. You asked for the average.
Mm-hmm. Yeah.
I did a piece of.
Yeah.
Well, technically, since there are infinite options with tails,
Mm-hmm.
that would mean that the average would be.
Mm-hmm. I think I agree that the average is infinite, but not for the reason that you're saying, because you can actually have options but only have a finite average. So just for an example, let's suppose that, okay, here's a really simple example. Let's suppose that I flip a coin infinitely many times, and then no matter what it lands, I win no money. Then there are infinite options, but I won no money.
Well, yeah, but in that case, no matter what happens, you win no money.
Okay, let's.
In this case, you can have a lot of money because it can keep multiplying by 2.
Right. Okay, yeah, I mean, in some sense, yeah, you can keep multiplying by 2, and the probability that you're going to get to keep multiplying by 2 is not too low. And so, how you would actually, let's say that x represents your winnings. So then, the expectation of x, so there's a 50% chance that you just stop.